control system, or which are an inherent part of the control system, will be connected with each other, and all those blocks will describe what they will describe the functionality of the control system. All those blocks which are essential requirements of that control system, so all those blocks will be describing, or they will be explaining, or they will be depicting what is the basic functionality of the complete control system. The entire diagram which we will be drawing is called a block diagram. So here in nutshell, in this technique, each subsystem in a control system is represented by a block. Okay. Then what will happen next? All such blocks, just a second, something wrong with this. All such blocks are connected with each other, are connected with each other, what to describe the functionality of the control system, of a control system. So very simple. What we'll be doing in order to find the transfer function, we'll be doing what? We will have a control system that will have each subsystems. We know what is a subsystem. We have explained it in the earlier classes. So all those subsystems will be connecting each other according to their functionality, that will be connected according to a sequence of operations that will be connected to each other. And then once we connect them each other, that will in totality describe the functionality of the control system. That's nothing but a block diagram. That's nothing but a the entire diagram is called the entire diagram is called block diagram. So a very simple definition. Then if we want to describe it more precisely, what basically consists of a block diagram? It will have a number of, it will be defined as the pictorial representation, where we have a blocks in terms of the pictures. It's a pictorial representation of the functions performed by the each subsystem. So each subsystem will be represented by a pic- picture, in a sense that it will be represented by a block, and each block will be describing its function, what are the functions performed by the individual block. And then there will be signal flow of signal. That means arrows will be going from one block to the another block. So a block diagram will be, in other words, described as a pictorial representation of the functions performed by each subsystems, and the flow of signals, how the flow of signals have to be arranged. The individual blocks in the control system are defined by their functions. Suppose individual blocks will be like a transfer function, it can be gain, it can be integrator, so on and so forth. So this is what the control system is. So we say that block diagram is a pictorial, sorry, uh, block diagram is defined as pictorial representation of the functions performed by each subsystem and the flow of signals. So it's very important. What is the function of the individual block? What is the function of that? And then how the flow of signals has been arranged. That represents the block diagram. The individual blocks in a block diagram, the individual blocks in the block diagram are defined by their functions. Are defined by their functions. Function, rather, we can say. For example, I can say individual block can have a transfer function, or it can have an integrator, it can have a gain, blah blah blah, extra extra extra. So many things can be there. So that will define a individual block. Now, figure I will show the individual components or a subsystem of a control system. Suppose I'll be drawing that. Okay. So R of S is input, C of S is output, and G of S everybody knows. Let's say individual block is a transfer function this time. So we have a transfer function. Okay. So in this case, we have already defined it. RS is input, then CS is output, GS is transfer function, then the system can be represented as, so system can be represented as output by input. We have seen this. Laplace transform is what? Transfer function. And then we can further write this. Output can be written as GS into R of S. So it's very clear. There should be no problem in this case. So that's the basic definition of the control system block diagram. So block diagrams in a nutshell, you have to remember what? In a nutshell, you have to remember it will consist of number of blocks. Those blocks will be arranged as per the signal flows. Each individual block will have its own function, and in totality, overall block diagram will describe the functionality of the control system. That's all. So we have input. I have taken individual blocks can be transfer function, integrator, differentiator, other functions. So it can be anything. Subsystem, we call it. Individual blocks can be treated as a subsystems. And for example, I have shown a transfer function. Input is this, output is this. This is the way we can get the input output relationship in this case. So next is, what are the advantages of block diagram representation? Next is, Advantages of block diagram representation of a control system. ठीक है, are as follows. Let's see what are those. So very simple. Like advantage number one, which we can say, see, it's easy to form the control system. We see control system will have a number of complex blocks in it. Subsystems will be very complex. There will be lots of subsystems. So what we do, we easily form the control system. How? A control system model can be easily formed. What? By connecting all the individual blocks. Individual blocks will represent a they will represent the subsystems. So according to their signal flow graph, signal flow means that how the arrangement of signal will flow. Suppose we were talking last about the simple control system of washing machine, how we will start the washer and then what the controller will do, it will compare that. So all those sequence of events will be related by the signals. There will be definitely a sequence of events in a food and beverage industry. We will have first the ingredients to be combined, and then lots of ingredients will combine. They will mix in a fixed ratio. Then they have to be put in the can, and then from the can they will be transferred for the this packing and other things. So every system will have a definite sequence of events, and that sequence of events means we are relating them with the signals. So that's what is the first advantage. So first advantage here is easy to form the control system model. Easy to form the control system model by what? By merely connecting, by merely connecting the blocks according to various signal flows. So you have subsystems, you connect them according to the sequence of events, you form a control system. So very easy to represent a control system. Easy to evaluate. Next is easy to evaluate the individual performance contribution. So when a control system engineer has to look into the, okay, what is the control system, what are the functionalities of the various blocks, so what he will do, he can easily evaluate individual blocks. That means individual subsystem which consists of a subsystem which will comprise or which will represent a subsystem. He can easily evaluate it, see it, and what will the performance of that, he can easily analyze all those things. So next is easy to evaluate the individual performance performance contribution by various subsystems. So next is that we have lots of subsystems in the control system. We can have numerous subsystems in the control system. And if a control system engineer wants, he can take an individual block subsystem and see what is the individual performance, that how we have to analyze that, and how we have to modify that, how we can improve its performance. So he can do it individually. He can take up all the individual blocks. Next is easy to assess the overall control system performance. So that's also easy to assess overall control system performance. So what you have to do overall, if you want to see what is the overall control system performance, how the percentage performance is there, how the individual blocks are there. So you can do it from output to input. You can see the if you have a precision set point is at some point in case of let's say in case of the automatic heating system or automatic room temperature control, then you can see the performance of each individual block as well as you can see the performance of the overall control system, whether that value set point we have set the value set point we have used in the control system and the actual output which we are getting, how much is the difference and how we can further improve that. So control system engineer can look into this and he can uh, even even make some modification for the improvement of the overall control system. Last is easy to examine functional operation of the control system, then to examine the physical system. See, what's the meaning of this? So, if you have something on the paper and you have already gone to the site and make you have mm, uh, you have made a model of that control system, then you have put everything on the paper and individual blocks you have identified and you have put them in the individual blocks. So this should be a subsystem, this is the subsystem, this is the subsystem, and then finally the signal should go from here, from one subsystem to another system that will overall give the performance of the control system. Then it becomes easier for a control system to easily it's for him to easier to examine what functional operation of the control system for that blocks, rather than to go into the site and look into things, and that will be a bit difficult because that physical system, in other words, he has to look a lot of things in the physical system. When he has put everything on the paper, then it becomes easy for him to examine and see what is the functional operation of the control system. So this is an also advantage of this. Easier to examine functional operational functional operation of the control system than to examine the physical system itself. It's difficult to examine the physical system itself. Okay. So these are the some of the advantages of the block diagram technique, how why we are using them. So there are lots of advantages and we should make use of these advantages while we represent the control system in terms of the block diagram. So definitions are there are some of the definition, then we'll go for the rules of block diagram, how we can reduce a block diagram technique. Then before that is the definitions in block diagram representation technique. Okay. So what are some of the definitions? Let's have a look. Very simple definitions. Number one, sorry. Number one, we have a summing point. So summing point is what? Sum itself indicates something. We have to add something. What we have to add? We have to add the signals. That's all. A summing point will include a symbol. It's a circle. There will be cross inside the circle, and there can be positive and negative. If there is positive, then all the signals will get added. Signals will be coming from the different blocks, different subsystems, and those, if the indication is in the summing point, which itself means that there should be a small representation is a circle, and inside the circle there is a cross. And if that signal goes towards the plus, then all the signals will be eventually added. If that goes to the minus, then signals will be subtracted. So that will be based on the functions of the individual blocks, the signals, how we have to manipulate or how we have to use the signals in the control system to overall consider its functionality. Based on the functionality of the control system, we will see that how we have to use those signals. So summing point is the point where various signals meet. It's the first point. It's the point where various signals meet. This should be very clear. The various signals are coming towards the summing point, and there can be a one signal, and then can be more than signals can meet there. I have already told it is indicated by what is the symbol of this? Indicated by a circle with a cross. That's the representation with a cross. The signals eventually to be added, the signals eventually to be added are or to be shown along with the plus sign. Hello, chair. Class चलन मैं क्लास चलन वो करे फोन से बात क्लास. Okay, are to be the signals eventually to be added or to be shown along with what? Along with the plus sign. Okay, and the signals eventually to be subtracted or to be shown with negative sign. Minus sign or negative sign, whatever. So what's the meaning of this one? Very clear. If we have number of signals that have to be added, then there in the cross there has to be plus sign. If they are to be subtracted, then there has to be a minus sign. Very simple. There's no difficulty in this case. Next is the various signals which will be meeting at the summing point must have same dimensions and same units. The various signals meeting at the summing points must have summing point rather must have same dimensions and same unit. So that's very clear. So if we are talking about something in the liters, then it should have a liters. Liters and kgs should not mix together. If we are talking about the meters and dimensions, something. So units and dimensions have to be same in the different control systems. Then only this type of system will work. Otherwise, It cannot work. A summing point performing addition operation a summing point which will be performing addition operations is called adder. And similarly, a summing point performing all subtraction all subtraction operation is called comparator or subtractor. So very simple thing. Summing point, I have told you in a nutshell, has to be represented by a circle. Inside that should be a cross. Signals which have to be added, there should be a plus sign, and signals which have to be subtracted must have a negative sign. And then it's mandatory to have the same dimensions and same unit while performing such operations. And next is that if the signals are to be added, that's called adder. If it is subtracted, then those are called subtractor. So let me draw a idea for you that how the summing point looks like. So inside the summing point, it will be a cross. Okay, now the signals, second cross will be there. Then what will be the flow of signals? Let us see. Let's see, this signal is going like this. Sorry. So next signal is going like this. And then we have a signal, output signal that's coming from this. Similarly, let me put for this. Okay. Now let this is an, sorry. Let this is here, it's a plus sign. So it's a plus sign here. Rather, I will make it by another color. This is a plus sign. This is a plus sign. Here it's a plus sign. Here this is a negative sign. So let us say the input is A and this another input is B. Then let's say C is the output and C will be A plus B. Let's say again input is A. Another input is B because signal there is negative. So this C will be this time A minus B. So this is the way a summing point has to work. This is the way. So first we will call it adder. And this is a summing point. Summing point. Second, we call it a comparator, and then it's also called a subtractor. So very simple. Signals which are with a positive sign will be treated as positive, with negative sign will be treated as a negative. So that's all. Very simple analysis for this one. Okay, next is important point is takeoff point, or we call it a branch point. Second, we have is a takeoff point, or we call it a branch point. Okay. So what's a takeoff point? It should be very clear. It's the point, you have to remember, it's the point from which the signals from a block. So it's a point from which the signal block से जब signal जाती है, it's a point from which the signals from the block goes concurrently. That means simultaneously to more than one block or summing points. So basically, what we have, this is sort of point from which a signal from a block will be going to more than one blocks or to a summing point. That's called a takeoff point. So let's write a definition of this one. So what is this? So because it's a point, so it's a point here. It's a point from which the signal from a block, I will add a page here. Signal from a block goes concurrently. That means simultaneously at the same time. Concurrently means simultaneously at the same point, same time to more than one blocks or summing points. Blocks or summing points, either it can go. Very simple. What's a takeoff point or a branch point? It's a point from which the signals from a block will go concurrently, simultaneously to more than one blocks or to more than one summing points. So let me draw this one for you now to understand this. Okay. Sorry. Just a second, my battery is down. Okay, so this is, I'll be drawing a takeoff point. So this, okay. See now here, here, this point, I will represent it by the red. This point here is a takeoff point. See, from this points, concurrent, from this point, concurrent signals are going to the other. Maybe it is going to other blocks or a summing point. We don't know here, but concurrent signals are going. That means more than one signal simultaneously are going from here. So this is a takeoff point. Now let's say this is an input. Just a second. Okay. So let me put it again in the red. Now let's say this is input R of S. Now this point again here is a takeoff point or a branch point. Now from here, the signals are going towards what? Signals are going towards more than one block. See, one is here and another is here. So let's call it G1 of S, and next two is G2 of S. Okay, so output here is C1 of S and output here is C2 of S. So that's a point called takeoff point, where from that point the signals are going concurrently or simultaneously to one or more than one block or to one or more than one summing point. So that's all that's about the, and some more we can add here. When a number of blocks are connected, the overall transfer function can be obtained by how? By block diagram reduction technique. So what's there also? When a number of blocks are connected, the overall transfer function can be obtained by block diagram reduction technique. So you have to reduce the block diagrams and get the overall transfer function. So you have to solve those in terms of, we will see that how we can, what are the different rules. Now let's say next is important. What are the rules we'll follow where we are using this block diagram technique reduction? How we can reduce the number of block diagrams into a one transfer function. So let's see what are the rules. So next is rules for block diagram reduction technique. So let's see what are the rules we have. Okay. Now rule number one. Sorry. First rule which we have. Okay. Rule number one is blocks in cascade or series. Blocks in cascade or the blocks are in series. Okay. Let's talk about this rule. Blocks are in cascade. So you should remember, when several blocks are connected in cascade, the overall transfer function is determined how? Is determined the product of the individual block transfer functions. I will repeat it again. If when we have numerous blocks that are connected in cascade, then how to find the overall transfer function? Because that's the objective, overall equivalent transfer function, rather, to be more precise. Overall equivalent transfer function can be determined by product of individual block transfer functions. So what the rule says? Rule says that when several blocks are connected in cascade, the overall equivalent transfer function is determined by is determined by product of individual transfer function. So individual transfer function, what will be? We have to multiply that, product it. Let's have an example here. Let's have a one block, another in cascade, another in cascade. Just a second. Okay, fine. So now we will have signals. So these are in cascade. One by one, they are in series. Okay. Now let's say this is an input signal R of S. Okay. This is output first C1 of S. This is output second C2 of S. This is the overall output C of S. Okay. Now this is a transfer function G1 of S. This is second transfer function G2 of S. Then this is third transfer function G3 of S. The cascade means they are connected in series. This is a series connection very clearly. So how we can say that we can obtain the overall equivalent transfer function just by the product of the individual transfer. That means overall transfer function should be C of S by R of S should be equal to G1, G2, G3. That's fine. So from the above figure, C1 of S, you can see here clear. First, take the first block now. Okay, here, one by one. Here, take the first individual block like this. Now, output is C1 of S, input is R of S. So here we can write C1 of S divided by R of S will be equal to G1 of S very clearly. Let's call it equation number 1. Similarly, if we take another block now, second input, output is C2 of S, input is C1 of S. So second we can write C2 of S divided by C1 of S is equivalent to G2 of S. Third output is C of S and input is C2 of S. C of S divided by C2 of S is equal to G3 of S. So these are the three equations we are getting from the above block diagram. Now, multiply equations 1, 2, and 3. One, 2, and 3. That will be C1 of S divided by R of S multiplied by C2 of S divided by C1 of S. Left hand side I am multiplying. C of S divided by C2 of S will be equal to G1 of S multiplied by G2 of S further multiplied by G3 of S. So that's the right hand side. So C1 and C cancel, C2 and C2 cancel. So on the left hand side, we will have C of S, that is the overall transfer function. You can very clearly see what is overall. Overall output is CF, overall input is R of S. C of S by R of S will be equal to individual multiplication of the product of the individual transfer function. That's what we have said. So you don't have to prove all these things while you are reducing a block diagram. You have to just multiply the individual transfer functions if this type of situation will arise. So that is G2 of S multiplied by G3 of S. So this is the first result we have got. I will box it in the red. Okay. I think this is fine. So let's move ahead. And the next is, oh, if we have to represent this in the block diagram, how we can represent this? So we can represent this like this. Sorry. We can represent this as like this. So this is your R of S. This is your C of S. This is individual. So transfer function will be G of S multiplied by G2 of S multiplied by G3 of S. Okay. So this is the representation in block diagram. So this is the block diagram representation above equation, which we have got this equation. So block diagram, we can represent it like this. Okay. So this was the rule number one. Let's go to the rule number two now. Now, rule number two says blocks in parallel. Rule number two. Okay. So rule number two is blocks in, blocks in parallel. Okay. So let's see what is now. Rule says that when one or more blocks are connected in parallel, so parallel connection, just electrical parallel connection is there. Uh, as we will show that, as we can show that in the figure also, the overall equivalent transfer function is the sum of the individual block transfer functions. So in case of parallel, what's happening? I will draw a diagram for that one. If one or more than one blocks are connected in parallel, then overall transfer function, equivalent transfer function, when we will determine, that should be simply the addition of individual block transfer functions, So let's draw the diagram first, then we can have a clarity in this rule. So okay. So what we have here, we have also just a second, please. Hello. Okay, now this is blocks we have. So let me draw a summing point here. This is the summing point. Okay. Summing point, everybody knows that it will contain a cross. Sorry. Okay. So this is the summing point. Now we will have the signals. Okay. So this clearly shows that the blocks are connected in. This clearly shows that the blocks are connected in parallel. Let's have a plus sign here, plus sign here, plus sign here. Now let's say this is an input. This is the overall output. This is individual transfer function number one, g of s, individual transfer function number two, g of g2 of s, and then g3 of s. Now, in this case, what we have, a rule says that when more than one blocks, when one or more than one blocks are connected in parallel, then the overall transfer function, or rather equivalent transfer function, is the sum of the integers. That means g1, g2, g3. That's all. Sum. So let's see how we can, from the above figure, from the above figure, we can write, see very clearly this output up to here, up to output, what is coming here. See, output of this is this one. I will, here you can see output of this block is here. Output of this block is here, but we don't know that. Output of this block is here. We don't know that. So what should be that? That should be, we know transfer function, we know input. Output divided by input is equal to transfer function. So output here, I can write, let us say output is this one, output by general function. Output by input R of S is your transfer function G of S. You know this, you know input, you don't know this. So your output at any stage should be equal to input into transfer function. So I can write, with the help of this formula, I can write here the output. So what I will going to write, output here will be input multiplied by the transfer function, that is R of S. Here it will be R of S. Transfer function individual block has G of S. Similarly here, R of S, G2 of S. Similarly here, R of S, G3 of S. So very clear, I have given you the idea. This is the output by input is the transfer function. So here is the output. We don't know that. We have two things. We can obtain the output. So now these signals are all going towards what? So I can write overall C of S, that is a overall output can be written as. So up to here, what is coming? R1, R of S, G1 of S. Here R1, sorry, R of S, G2 of S. So I can add these signals. So up to here, you can very clearly see all are summing signals. So I can write C of S can be written as R of S into G1 of S plus R of S into G2 of S plus R of S into G3 of S. So this is what the signals are coming towards the summing point. So from here, what I can do, I can take this R of S common. R of S common will be G of S plus G2 of S plus G3 of S. So if I want to obtain the overall transfer function C of S by G of S, that should be equal to sum of the individual transfer functions when blocks are connected in parallel. That's what the rule says. So I'll box this rule also. I hope this is clear. So I think we'll stop today here only, and then we have few more rules. It may take one more class. We can stop then later on. This other rule is also going to take some time. Tanzeeb,
Yes, sir.
is it clear or not?
Yes, sir. Clear, clear.
हमारे पास टाइम है अभी, मेरे को 6 मिनट है हमारे पास ना.
सर 12:47 हो गया.
ओके, मुझे लगता था 2-3 मिनट हैं तो वी कैन डू वन मोर रूल. अगर आपका क्लास है इसके बाद तो देन इट्स अ प्रॉब्लम.
नहीं सर, इसके बाद है ना हमें ब्रेक, तो नमाज
कैन वी
है.
डू वन मोर रूल हियर और नो?
सर अब आज जितना ही करेंगे.
ओके फाइन.